The world is full of sequences. Enter long short-term memory networks, or LSTMs, a specialized type of recurrent neural network designed to excel at processing and making predictions based on sequential data. LSTMs possess an internal memory mechanism that allows them to retain information over long periods, making them ideal for tasks where traditional RNNs struggle. Imagine trying to predict the next word in a sentence. LSTMs operate similarly, using their memory to understand not just individual data points but also their relationships within a sequence. This ability to learn long-term dependencies has revolutionized fields such as natural language processing, speech recognition, and time series analysis.
Before we dive into the intricacies of LSTMs, let's first understand why traditional RNNs fall short when dealing with long sequences. RNNs are designed to process sequential data by iterating through each element in the sequence and maintaining a hidden state that captures information from previous elements. However, traditional RNNs suffer from a critical limitation known as the vanishing gradient problem. As the network processes longer sequences, the gradients used to update the network's weights during training can become increasingly smaller. This diminishing gradient makes it difficult for the network to learn long-term dependencies as information from earlier elements in the sequence fades away. Imagine a game of telephone. As the message is whispered from person to person, it becomes increasingly distorted. Similarly, in a traditional RNN, information from earlier time steps gets diluted as it travels through multiple layers of the network.
LSTMs address the limitations of traditional RNNs by introducing a unique memory cell that can store information over long periods. This memory cell acts as a gated unit, selectively remembering or forgetting information based on its importance. Instead of simply passing information from one step to the next, LSTMs regulate the flow of information through specialized gates, ensuring that relevant information is retained while irrelevant information is discarded. At the heart of the LSTM cell lies the cell state, a memory pathway that runs through the entire chain of LSTM units. This cell state acts like a conveyor belt, carrying information from one time step to the next with minimal modification. Information is added or removed from the cell state through carefully regulated gates. These gates control which parts of the input sequence are remembered and which parts are forgotten, enabling the LSTM to learn long-term dependencies effectively.
Section 4. Inside the LSTM cell, gates and states. To truly grasp the power of LSTMs, let's take a closer look at the inner workings of an LSTM cell. Each cell comprises four main components: the cell state, the input gate, the forget gate, and the output gate. These components work in harmony to selectively process and store information, enabling the LSTM to learn long-term dependencies effectively. The cell state, as mentioned earlier, acts as the memory bank of the LSTM. It carries information from one time step to the next, allowing the network to retain context over long sequences. The input gate determines which new information should be stored in the cell state. The forget gate decides which information should be discarded from the cell state. Finally, the output gate determines what information from the cell state should be outputted at the current time step. Section 5. LSTMs in action real-world applications. LSTMs have become indispensable tools in a wide range of real-world applications, demonstrating their prowess in handling sequential data across various domains. Let's explore some prominent examples where LSTMs have made a significant impact. Speech recognition. LSTMs have revolutionized speech recognition systems, enabling more accurate and natural-sounding voice assistants and transcription services. By analyzing the sequential nature of audio signals, LSTMs can effectively capture the nuances of human speech, such as intonation, pauses, and accents. Language translation. Breaking down language barriers is another area where LSTMs shine. They excel at capturing the context and meaning of sentences, allowing for more accurate and fluent translations. Time series forecasting. Predicting future trends based on historical data is a crucial task in various industries, from finance to weather forecasting. LSTMs, with their ability to learn long-term dependencies, are particularly well-suited for time series forecasting. By analyzing past patterns and trends, LSTMs can effectively predict future values, enabling businesses to make informed decisions and optimize their operations.
Section 6. Looking ahead, the future of LSTMs. LSTMs have undoubtedly revolutionized the way we process and analyze sequential data, but their journey is far from over. As research in deep learning continues to advance, we can expect to see even more sophisticated and powerful LSTM-based models emerge. One promising area of research is the development of attention mechanisms, which allow LSTMs to focus on specific parts of the input sequence that are most relevant to the task at hand. This selective attention mechanism enhances the model's ability to understand long-range dependencies and improves its overall performance. As we continue to explore the full potential of LSTMs, we can expect to see them playing an even more prominent role in our lives, powering intelligent systems that can understand and interact with the world in increasingly sophisticated ways.